Alright, so let's look at our monotonic equation and see what we have. Now, so here's the equation. Epsilon is equal to sigma over e plus sigma over k prime to the 1 over n prime power. We're going to define a new function, capital F, of sigma that's going to be our equation for the Ramberg-Osgood description of the material minus the epsilon term. Okay, so the terms that we know are E, K prime, and N prime, a known level of strain, epsilon, and we want to find the sigma that makes this work out. We have our material properties that are known, capital E, K prime, N prime, and we're going to use a strain of 2500 microstrain. Now the next thing we need is the derivative. So we'll call this derivative of capital F with respect to sigma. Of course, the derivative of the first term is going to be 1 over E. Okay, we're going to have 1 over N prime, and leave a little space here for a reason, sigma over K prime to the 1 over N prime minus 1. Then we need the derivative of the term in the brackets, which would be 1 over K prime. Derivative of the constant strain is going to be 0. Okay? So we have this set up. Now I'm going to try to illustrate this process by hand, then I'm going to show you my spreadsheet for this. So I'm going to take an initial guess. You know, this picture over here kind of illustrates what this graph looks like. It's just a kind of a cartoon sketch. It's a lot steeper than this, really. But the point of me drawing this is to say that if we were to select a certain value of strain, it corresponds to a certain value of stress. There's a one-to-one correspondence in this equation. So this is a very nice type of equation to use Newton-Raphson iteration with. So I don't know what this is going to be, but just based on my experience, I would expect somewhere around 350 megapascals. It might give us 2500 microstrain for these material properties. Alright, so my new guess is going to be a modification of my original guess. And we're going to have minus, let's see, F of sigma divided by dF of sigma. dF prime, yeah, dF of sigma. Alright, so I won't write that all the time. So I need to find the F of sigma value. So I'm going to plug in these. I'm going to do this one by hand, and then I'll switch over to a spreadsheet. So I have my 350 megapascals divided by my modulus of elasticity, 210,000, and I got my 350 divided by 1800 to the 1 over 0.2, which is the 5th power. I'm going to add those two terms together, and I get almost 2,000 microstrain. So, you know, I'm probably in the neighborhood of around the right value for this. So now I'm going to subtract off 2,500 microstrain, and I get a pretty small number. Now, this number is negative. We need to keep that negative sign in here because this will end up with a positive contribution, probably, depending on the sign of the slope. 0, 0, 0. There's 3 zeros, and I'm going to write a lot of digits. 5, 5, 5, 3, 7, 6. You know, but there's really only there's only 6 significant digits in this expression. Okay, now I need to calculate my dF. So I just have 1 over the modulus of elasticity. I'm going to take the term in the brackets first. 350 megapascals divided by 1800. Now it's to the fourth power. I'm going to divide it by 0.2, and I'm going to divide it by 1800. And then I'm going to add those two terms together. Okay, so I get kind of a tiny number. Let's see, 1, 2, looks like 5 zeros. And then 8733. Okay, I'm leaving these in my calculator. So there's going to be more significant digits than that, but I'm just not going to write any more out than that. Okay, I'm going to take this division, and the term in the brackets turns out to be minus 63.6. So my new guess is going to be 350, then the minus a negative 63.6. Okay, so this turns out to be 413.6 megapascals. Okay, well, is that good enough? Well, I don't know until I do one more calculation at least. So I'm going to make another new guess, and it's going to be 413.6 minus, okay, now I'm going to put in 413.6 divided by the modulus of elasticity. I'm going to take my second term, okay, and if I did all my calculations right, I get a small positive number this time. And now I need to take my 1 over e for my derivative. My 413.6 divided by 1800 to the fourth power divided by 0.2 divided by 1800. I'm going to add the term together, and then I get another small term, 0.000012505. Take that ratio, and I have 8.8, so 413 minus 8.8, I get 404 MPa. Let's do this again. My new guess is going to be 404.8 minus, okay, 404.8 divided by 210,000 to take my F of sigma term. .8 divided by 1800 to the fifth power. Subtract off 2500 microstrain. Okay, now I get a lot of zeros here. 1, 2, 3, 4, 5 zeros. 2816, and then take my DF, and I get a little number down here. I'm going to divide those two numbers, and I'm going to subtract. So now my difference now is only 0.2 megapascals. Okay, so I went to 404.8 and I have 404.6. So I really think that the actual number for this is probably very close to 404.6 or 7. And what you can do is you can keep iterating this until you get to a residual that's less than, pick a number, 0.1 megapascal or 0.001 megapascal. But look how fast that converged. That converged with only 3 iterations of this. The Newton-Raphson technique is what is called superconvergent. That means it'll converge very quickly. Now let me show you my spreadsheet that I did for this. And while we're here, let me paste my equation in. Alright, so here is my modulus of elasticity, my K prime, my N prime, and my strain value, my initial guess, my term 1, I broke this up into 2 terms. That's the sigma over E. This is my F of sigma term. And then my term 2 is the one with the exponent, sigma over K prime to the 1 over N prime power, minus epsilon. Okay, so that incorporates that term 2. I add those together. That's my F of X. Here's my term 1 primed, so that's the 1 over E. And here's my term 2 prime, so 1 over N prime, 1 over K prime, sigma over K prime to the 1 over N prime minus 1. And this is those 2 terms added together. This is the ratio. Okay, so here 63, and then here's my new guess. So let's see if I did it right. I said 414. Okay, yeah, so that's looking good. So I put in here 414. My new guess is 405. Put in here 405. So it's looking like within, the rounding up, the answer is about 405 for the value of stress that corresponds to a strain of 2500 microstrain. I will give you this spreadsheet. You can play around with it if you'd like, but it's just to illustrate the Newton-Raphson iteration technique. Alright, so let's set up the other 2 equations, and we'll do that over here. So let me save this. For the branch equation, we have delta epsilon. I always like to write it this way first. Delta epsilon over 2 is equal to delta sigma over 2 divided by E plus delta sigma over 2 divided by K prime to the 1 over N prime power. Now we could multiply both sides by 2, and let's go ahead and do that. And we're going to find our F of delta sigma as delta sigma over E plus 2 times delta sigma over 2 divided by K prime to 1 over N prime power, then minus delta epsilon. Alright, keep an eye on me, make sure I take my derivative right. It's going to be 1 over E plus 2 times, I'll leave a little space, delta sigma over 2 divided by K prime So the 1 over n prime power minus 1. And then I'm going to have a 1 over n prime. And then I'm going to have a 1 over k prime. And then I'm going to have a half. So I think we can simplify this down a little bit. All right, and so we're going to keep our same material properties. And now if we have a constant amplitude strain, so I go to 2500 microstrain, and then I go down to minus 2500 microstrain. Now my change in strain from here to here is going to be 5000 microstrain. Okay, I'm just going to copy the monotonic one, and I'm going to put branch. I'll get rid of this picture. Let's see, let me find, there it is, my sketchbook. I'll paste this picture in here so I have those equations for reference. And I'm just going to modify this one here and move my tablet out of the way. Same material properties. Now this is actually going to be the delta strain. And it's going to be 5000 microstrain. Let's go back. Let's change that guess. Okay, so my term 1 is going to be the delta sigma I'll make sure that it's clear that's a delta sigma. It's going to be my delta sigma over E. Okay, so that looks good. My term 2, I'll get to modify this, is going to be my delta sigma over 2 divided by k prime to the 1 over n prime, but I need a 2 times right here. And I think that will do it. Okay, my term 1, let's see, let's check on this one. Minus the delta strain. Yeah, all right. So my prime term 1 would be 1 over E, that should be the same, and my prime term 2 is going to be 1 over n prime, 1 over k prime, and I need to modify this, so I divide that by 2. I'm going to save that spreadsheet. Okay, so the new guess is 1012. So I'm going to try 1012. Now my new guess is 861. new guess is 813. 809. Stays at 809. Okay, so what this represents then is that it represents the change in stress from where we were at the end of the first monotonic part of this. So let me go back to here, get my tablet back. We started off at 0 stress and strain. We went up here to 2500 microstrain, and we had a stress level of, what did we say? It was 404, I think. Let's just leave it 404. Keep the digits that I have in my spreadsheet. It's either 404 or 405, because I can look back at the spreadsheet and see. 405. I had a change, a delta sigma of 5,000 microstrain, and that corresponds to a change in stress of, we said 809. We're on the branch equation 809. So we're at plus 405. We take away 809. We're at minus 404. If we do this again, we would get the exact same value, because now we're upsloping 5,000 microstrain. So we would take minus 404 and we would add 809. It would get us back here. If I were to add a couple more digits to this, a couple more behind the decimal place, it's probably like 405.5 or something like that. And so then we have a stabilized hysteresis loop. Okay, so this is what I want you to do. I want you to be able to have a computer program that either uses a Newton-Raphson technique or a built-in root solver. And I want you to be able to calculate these endpoints. It would be really nice if you just had it also just graph out or print out the values to graph in Excel for these hysteresis branches. All right, there's one last one I want to talk about, and that is the strain life equation and its variance. Okay, so let's write out the strain life equation. The strain amplitude is equal to sigma f prime over E, 2nf to the b, the Baskin equation, plus epsilon f prime, 2nf to the c. Fatigue strength coefficient, fatigue strength exponent, fatigue ductility coefficient, fatigue ductility exponent. Let's leave this as the amplitude. All right, so let's define our f. Now it's a function of 2nf. Is going to be sigma f prime over E, 2nf to the b, plus epsilon f prime, 2nf to the c, minus the strain amplitude, or the range, over 2. Our df by 2nf. Okay, so think of this as a single symbol. Don't think of it right now as 2 times nf. We'll deal with that later. What we're going to do is we're going to find the number of reversals that corresponds to a certain strain amplitude. All right, so let's see. We have sigma f prime over E. We're going to have 1 over b. We're going to have 2nf to the b minus 1. we're going to have epsilon f prime, we're going to have 1 over c, we're going to have 2nf to the c minus 1, and these should be our terms right here. So I'm going to grab this, and I'm going to paste these into my spreadsheet as well. And I had a previous version of this on our box account. I'll give you this one as well. But the previous version had actually a little bug in it. So let's go through this and make sure we have everything we need. So here is my modulus of elasticity. I'm using 208,500 this time. Got these out of the book, I think. Sigma f prime, epsilon f prime, b and c. And here's my strain amplitude of 007182. Okay, so my term 1 is this term, sigma f prime over e times 2nf, this is reversals, to the b power. My second term is epsilon f prime times 2nf to the c power. And then my third term, my strain amplitude, this should actually be a minus right here. Oh, well, if I put that a minus, I need to make this a plus. Okay, so my total f of x, or f of 2nf, is this term and this term and this term. Okay, here's my derivative. Let's see, let's check and make sure I've got it right. Sigma f prime over e times, well, let's see, times g4. Oh, you know what? I made a mistake. I got carried away with my previous analysis. I need to fix this. Let me go back to this page. I said keep an eye on my derivative here. So this should be a b, and this should be a c. Let's recapture this. Okay. Sigma f prime over e times b, 2nf to the b minus 1. And this one is epsilon f prime times c, 2nf to the c minus 1. Okay. Alright, so let's take a guess at this. And let's say I'm going to guess that this would last 4,000 reversals under this strain amplitude. It's a pretty hefty strain amplitude. Okay, it comes back with a new guess of 4838. I can put that in here. It comes back with a new guess of 5016, 5022. And that looks like that's the answer. So under these conditions with that strain amplitude, and let's check strain amplitude. That would be the delta epsilon over 2. So the strain range would be twice this. Then I have this value for number of reversals. Let's put a little note in here. Note amplitude is half of range. Okay. And then we'll put a little note here. Note cycles is half of reversals. Alright, so I think I showed in a video before me using the spreadsheet, and I kind of noticed that it took a long time to converge. That's because I had a mistake. I left off this third term, I believe. But I think we're in good shape now, and I'll upload this to our box folder, and you can take this and modify it. If you're using Excel, you can use a goal seek or different things. But I do want to illustrate the Newton-Raphson technique. Okay, so this is the second part of the video that talks about kind of the theory of Newton-Raphson iteration. The next part, the next video, I'm going to try to do the rest of this is to have a computer program that will do all of this, given a certain strain level, find the branches, the appropriate branches of the hysteresis loop.